Okay, thank you. And thank you for coming. It's a pleasure to be here. So I want to talk about the route to turbulence in fluid flow. So I think it's generally known turbulence is the great unsolved problem of classical physics. And there are many ideas about what the solution to the turbulence problem would be. I want to talk about something very specific, which is how do flows become turbulent? So you have a flow that under some conditions, some low Reynolds number, some low stresses, the flow is smooth and laminar, and then as you increase some control parameter, some flow rate, the fluid becomes turbulent. And that's one important aspect of the turbulence problem, to understand how you make a transition from laminar flow to turbulence. And the thing is, what I'm going to focus on in this talk are this class of problems, wall-bounded shear flows, such as, and I've drawn the same ones here because I'll want to point to them from time to time, particularly flow through a pipe, but also flow through a channel, or Couette flow where you have just simply a shear of fluid between parallel plates. These kind of flows, there's been a fundamental change in the way in which we understand the onset of turbulence in these flows that has taken place in the past 10 to 15 years. And that's what I wanted to tell you about. And to kind of motivate it, I want to say a few things. I was under the impression from earlier today, many people know these kind of flows better than I do, and I realize maybe not everybody, and if you don't know about them, it doesn't really matter. But there are flows that are flow between concentric cylinders, the Taylor-Couette problem. So I have an inner cylinder here, and I'll just consider the case where I'm going to spin the inner cylinder, have an outer cylinder, and there's fluid between those two, and that's a fluid dynamical situation. Or you can have Rayleigh-Benard convection, where I have heated from below, cooled from above, a fluid layer in there, and I have some control, which is the temperature difference. And in these cases, starting in the early 20th century, there was huge success in understanding how these flows become unstable, and then eventually, through the later parts of the 20th century, how they become turbulent. All right? And in the simplest case, and again, I don't want to spend too much time on this, but the reason why, at least in most parameter regimes, not in all parameter regimes, this works is because as you adjust the parameter, you have some amplitude, it doesn't matter. I'm just trying to distinguish different states here, it doesn't really matter. I have some control parameter, temperature difference or speed of the inner cylinder. I can find a place where I can actually do an expansion, a linear expansion, and I can find actually an instability. I can find a transition point, and I can often do it with paper and pencil. And then I can do some weakly nonlinear theory and understand what comes out of that bifurcation. And then if I'm really good, probably turning to a computer, I can continue on and I can find, in fact, that this becomes unstable again to yet another state, et cetera. And then applying some dynamical systems theories, some symmetries, ideas like this, you can eventually understand that it will become turbulent. Sorry, ran out of room. At least in a weakly nonlinear sense of chaotic dynamics. Okay, and this problem is very well understood now. I mean, there are many open questions, but that general program is well in hand. And it's been extremely successful and extremely influential, and really outside of fluid dynamics as well, as I think people know. And let me just point out something so I don't fail to say, it's not always, this is what would be called the supercritical case, where the new branch that appears is stable, from a stable to a stable, but it can be the case that it turns backwards. I'll try and draw it this way, where this actually turns backwards and then eventually stabilizes. This would be a subcritical case or weakly subcritical, but that still falls into this approach to understanding the onset of turbulence. Okay. Now, the success of that approach has actually been somewhat detrimental, I believe, to understanding this. That I think a lot of time was wasted by people, including myself, trying to take that picture and contort it to what happens in these flows. And that just is a mistake. It's not the way to think about it. And so one way to get to kind of motivate this is with a question, is what is the critical Reynolds number for the onset of turbulence in a pipe? See, over here I told you, in both of these cases, we know what it is. We know how to compute it with basically paper and pencil. G.I. Taylor did this in 1923. He found this first critical point. And it's what, and you can reproduce it in an experiment. People can reproduce it in all kinds of calculations. And everybody agrees what it means and how to find it. So Reynolds knew that this is pipe flow. He knew that the critical Reynolds number for pipe flow, I'm not telling you quite what it means, but he knew it was about 2,000 in the way you would define Reynolds number for a pipe flow. Anyway, he knew what it was. And then in the 20th century, there were some results. Rada approximated it as 2,300. And then people, largely because of Tom Mullen's work, began to be reinterested in the pipe problem and these wall-bounded shear problems, and to look at them, very, very carefully with the kind of rigor and that people had looked at these problems. And so then in the 21st century, people began to look at this more carefully, and these are the values that were coming out of studies. And just to say, I mean, they look funny, but these are serious studies. These are serious scientists. These are published in high prestige journals, and people simply could not agree what the critical Reynolds number was for this flow. Okay? And what it tells you is there's a lack of understanding of what we're doing. Okay? It's not that people are stupid. I mean, these people are really bright. And just to emphasize something, that it really, the fact that you could have looked in Wikipedia, and this is something that went around at the time in this community, is Wikipedia was full of all kinds of different answers depending on what particular article. Nobody knew what the critical Reynolds number for pipe flow was. And it's surprising how many places in Wikipedia this comes up, because people say, as in pipe flow, the critical Reynolds number is, and then they could just quote whatever they remembered, and it didn't seem to have a well-defined value. Okay. All right, so I want to discuss this, and I would like to present it in a way, look, you can read the papers. I mean, we've written papers on this, and they're accessible, and you can just read them. I'd like to present it a little bit different than what you would just read in a paper, because it is a talk format, so I'd like to do that. So let me just start with Reynolds. This is not Mr. Reynolds, that's Mr. Foster. But that's the pipe, and just that's why I draw it that way. That's why most people, that's where the pipe is. This experiment still exists in Manchester. You can go and you can get your picture taken on it. There it is. That's me. I don't, you can't quite tell. All right. But anyway, so this is what Reynolds told us, that at low Reynolds number, this is a streak line, that's di. At low Reynolds number, the flow is laminar. You get a straight streak line. At high Reynolds numbers, high flow rates, let me just say, I haven't defined Reynolds, maybe I should. The flow is very quickly after the inlet, it becomes fully turbulent. You have a turbulent pipe flow. But in between, you have an intermittent regime where you see these, what he called flashes of turbulence. And let me say now, because I forgot to write it on the slides, I'm going to refer to these as puffs. And I can't stop myself, because that's what we say. So just if you see these, if I use the word puffs, that's what I mean by these little patches of turbulence in a pipe, okay? So that's what we know from Reynolds. And the thing is, what differs between these flows and this flows is that in these flows, we have a finite amplitude instability, all right? Without laminar flow first becoming unstable. And in fact, let me just illustrate that here. This is not a perfect plot. I'm sorry, I didn't. This is Reynolds number. And as you can see, it's on a logarithmic scale. You just have to remember that, okay? And this is the friction factor, which you think of as the pressure drop you need to drive a given flux, okay? It's a measure of the resistance of the flow to forcing, all right? And that's also on a logarithmic scale. You can't tell that. And then there's a laminar branch and a turbulent branch, okay? And these are disconnected, okay? All right, and this branch, as far as we know, never undergoes a linear instability. That laminar flow, the laminar solution to pipe flow exists for arbitrarily high Reynolds number and is stable. Okay, it never has a bifurcation, so it is not at all in this class of problems. Okay, so but this has been known for a long time. So it's a finite amplitude transition. Okay, it's a finite amplitude transition, and this is my favorite example of a finite amplitude transition that we can all do. You know, it's a Coke can. It's under pressure, all right, but it's stable. There's fluctuations going around. There's trucks on the road and so forth. And it will just stay in this state indefinitely, right? So you're here and you'll just stay there indefinitely. This is laminar flow. You introduce a perturbation and you transition to turbulence. Okay? A finite amplitude perturbation is necessary, and then you transition. And it's an abrupt transition, and it's dramatic. Okay? So this is the way you should think about it. I have a control parameter, which is pressure, and I have a state, which is the inverse height of the can. Okay, so I have my laminar state, which is the uncrushed Coke can, and I have the turbulent state. And there's a threshold depending on pressure, and if I cross that threshold with a finite perturbation, I jump to the crushed state. But you notice that these two are very widely separated. This is nothing at all like this, and it's not a weakly nonlinear theory. You're not going to understand the crushing of a Coke can well through this method. Now, that's not entirely true. People do. Oh, let me not get into that. All right. Let me just say that for our purposes, that's not a good approach.
Sorry, I didn't interrupt. I was just trying to understand the difference in the geometry. The Taylor-Quid flow seems, at least in some limits, it should go over to the
You're right. That's why I only am rotating the inner cylinder. That's right. If you start, because then if you start rotating both, you can definitely put it into those limits. That is exactly right.
So, but then you're saying if it weren't rotating, then this has this behavior, the one with...
I'm saying that if you only rotate the inner cylinder, it does this.
The moment you start rotating...
If you start counter-rotating, look, if you do exact counter-rotation and work in a narrow gap, then you're going to be in this limit, and it's going to be subcritical. And there, in this case, by the way, we know it's provable that there is no linear instability. In this case, we don't know, but it almost surely is the case. Okay, so what we know from this then is these subcritical, they're called subcritical shear flows, these wall-bounded flows that are in this case, that there's, as I've tried to draw here, there's a laminar branch and a turbulent branch. Here I've drawn with friction factor. On here I'm just drawing as a kind of generic bifurcation diagram, and that there's a finite threshold that you cross, and then you get a very, very different state. Okay, so that one is not a small perturbation of the other, and there doesn't seem to be much in between. And that transition where you begin to see turbulence, and I didn't label it on here, is typically of order 1,000 in any usual definitions of Reynolds number. It varies between the particular flow, and again, depending on how you define Reynolds number, but it's of the order of 1,000. Just to say, I don't want to. Okay, so what we've known, it's been known, Landau was the first person I know that said this. He said that that the route to turbulence in pipe flow in particular, he said it's a hard transition. It's a subcritical or hard transition. Did I use that word hard? I used it someplace, okay? Landau used this and he understood very well. The thing is, it turns out that that's incorrect. And this is what took so long for people to understand and understand the right way to look at the problem. So despite the fact that this diagram is correct, and what I've drawn here is correct. You have laminar flow that never becomes unstable. You have a disconnected turbulent branch, which is in no way close to this branch. There's no measure in which these two are close, no meaningful measure. Nevertheless, the transition between laminar flow and turbulence is a continuous transition, okay? It has well-defined, it obeys very specific universal exponents with well-defined critical points. And this is what we now understand, okay? So that's what I'm going to tell you about. Okay, I have to tell you a little bit about intermittency, about this state. All right, so this is just a picture of, I'm not going to go through all these in detail. These are just a variety of different shear flows. It just doesn't happen in these three. There are a variety of cases of shear flows in which when you look between the fully turbulent state and the laminar state, you see these states here exist as long-lived intermittent turbulent states. Oh, by the way, just to say, you're looking at an orientation generally perpendicular to the walls. And the length scales are large, these are details, but that's about 20 times the gap between the cylinders. And these are dynamic. These are so-called turbulent bands. It's like this. There's a patch of turbulent, laminar, and these things here, let me just replay this. You know, this is really turbulence. There's really dynamics here. This is not a steady state, but it forms these kind of stripe patterns, this intermittent pattern. That's a whole nother talk to talk about these patterns. I'm not going to do that here. If you look, this is very much sped up movie. This is an experimental movie. This is turbulence, and that's laminar flow, and it's intermittent. And it'll just stay like this for as long as you watch it. Okay, it's an intermittent mixture of turbulent and laminar flow. And that is pretty much, in these flows, almost always observed between a fully turbulent case when you're up on this branch and the laminar branch. In between, there are these intermittent, this intermittent flow, but where you have a mixture of turbulent and laminar flow. Yeah.
About the telecoil flow.
Yeah.
You know, experiments made by Donald Coase a couple of years
Yes.
long ago. They found multiple solutions.
Yes, he did.
Different values of the Reynolds number, both on the inside and the outside pipe. That actually complicates the process of telecoil because again, as I understand.
Okay. Well, that too is a long story. So yeah, as far as I know, nobody ever won. You probably know of the Don Coles cube of the where you measure the different states, and you win the cube if you explain it. Anyway, so as far as I know, it's gone unclaimed, that prize. Yes, that's a complication. I would still put it in this category of things. It's things we can certainly now understand pretty well with a computer, and that there are kind of low-dimensional phenomena. They're not kind of the statistical phenomena that I'm going to be describing later. But yes, even within this, there are a lot of complications with multiple solutions, et cetera. Yeah.
In your FRE
Yeah.
diagram, I understand that the laminar state is your analytical solution.
Yeah.
Is there one turbulent state? I mean, when you draw that line, what do you mean?
What I mean is that if an experimentalist comes along and measures friction factor, they will lie and does it with good statistics over sufficient long periods of time, et cetera. They will lie on a curve that people now, everybody's data agrees. That's what I mean. And yeah. And things are known about that, although there are arguments still about that.
So it still represents many states, right?
It represents
It's not like the single state that the laminar.
That's right. Well, it's a when we get to the end, if I get to the end, which I probably won't, maybe it'll be that state. I consider this, from my point of view, simple.
Okay.
Because you can read it in Steve Pope's book.
Okay.
Anything you can open up a textbook and read in about 5 pages, I'll call simple. Okay. So in that sense, I believe it's large. All right, so here's what we have. What I'm telling you is we have laminar flow, we have fully turbulent flow, which you could read in Steve Pope's book if you haven't done it yet. You can read that in Steve Pope's book. And in between we have this, which I will claim, for a long time it was thought just to be due to dynamical noise, but we know it's fundamentally really a dynamical state of the system. I want to just organize it this way. So control parameter, which is Reynolds number, I'm just going to use turbulence fraction, which is the percentage of the flow that is turbulent after initial conditions have passed, after it's reached some equilibrium. All right, so laminar flow has no turbulence, so its turbulent fraction is 0. If you have fully turbulent flow, kind of by definition, its turbulence fraction is 1. The flow is everywhere turbulent. But these intermittent states, they have a non-trivial turbulence fraction. Some of the flow is turbulent and some of it's laminar. Again, you have to run this for a long time, run your experiment for a long time, run your simulation for a long time, and get an equilibrium value, and then you're allowed to put a point there, okay? So it's an equilibrium value. It does have an equilibrium, and you can find it. And it grows. And so the thing is, below here, turbulence could exist, but only transiently. Asymptotically, there will be no turbulence. Above some critical value, there will be turbulence, and associated with this is critical phenomena. I haven't explained any of that yet. That's what I'm going to tell you, okay?
And this you're saying is very different from
that, because of the complexity of this, spatio-temporal complexity. You go from something that is simple to something that is spatio-temporally complex right from the onset, which is very different from that picture. And by the way, it's also, you have to work in a thermodynamic limit where the system size is infinite and the timescales are infinite. And so that's, makes difficulties.
Sorry, is there an analog of a turbulent fraction in that picture?
Yeah. Well, there's obviously Nusselt number scaling is a function of Rayleigh, which is probably one of the big important problems. So there are things like that, but it's not exactly turbulent fraction. I'm thinking about something that really you can distinguish turbulent and laminar, but yeah, let me think about that.
Is that a simple volume fraction when you say turbulence fraction?
You mean, does everybody agree what that should be? You're saying, does everybody agree what the definition?
What is it exactly? So if you have a domain, a flow domain, is it just the volume fraction?
Yeah, it's just a volume fraction of what you're defining in turbulence. And then there's a question of whether you precisely have everybody agrees on that same definition of turbulence. I'll just say for those, if you're doing critical phenomena, that doesn't matter. As long as you don't have something that's non-smooth, you'll get the same critical exponents for any definition of turbulent fraction. That's the beauty of that kind of critical phenomena. Okay, so here's the way you should think about it. So let's ask you a question. So is turbulence in a pipe sustained at Reynolds number 1,900? So who thinks yes and who thinks no? Oh, okay. So let me give you a hint, because you probably don't know much about this. So let's show you an experiment. So this is an experiment. It's Reynolds number 1900. This is by Tom Mullen and George Pixino. And there's a pipe there, and they introduced a perturbation, and it's running down the pipe. And here's a simulation by Microvilla, also at Reynolds number 1900. And you see there's this patch of turbulence. Again, it's localized. It's this puff. So here's laminar flow, and there's laminar flow. And this thing is moving downstream. It's chaotic, is it? But it's really a fixed intensity. You can see it's really a fixed intensity. The camera's moving downstream. It's not speeding up or slowing down much. So it looks really, it's pretty stable. All right, so that's at Reynolds number 1900. So we say yes. And then so what we do next is we're going to lower the Reynolds number and see if it's still stable there, right? No. Okay, I tricked you. So the thing is, if you wait longer, let's wait a little bit longer here. So it looked fine, it looked stable. Oops, it wasn't. Okay, so all right, so the answer was no. Okay, so what we're going to do is increase the Reynolds number and do the next case. Okay, both ideas are bad ideas. The point is it's statistical, and looking at one realization is not going to tell you the answer. All right, you have to do multiple realizations. Okay, it's a statistical phase transition. So this brings me to the world of statistical phase transitions, and this Janssen and Grassberger published papers on this in the 1980s and made conjectures about systems, and this would apply to heterogeneous chemical reactions, to forest fires, to flow through porous media, and flu epidemics, okay, and many other things. And just a quote from the paper, it suggests another type of universality comprising all critical points with an absorbing state and a single order parameter. So I have to explain all those words, but that's the idea, is that there's a kind of universality associated with these systems, and you'll notice you can just see, well, let's look at the forest fire example. It's not like that, okay? It's not like that. It's a different kind of example. Okay, and Yves Pomeau realized in the 1980s, not long after Janssen and Grassberger published their work, that these subcritical shear flows would also be of this type, and they ought to also exhibit that kind of universality. And this was taken up by the group in Saclay. Unfortunately for them, I mean, they had really the right ideas, but they were too early, and their system sizes would turned out to be just very, very much too small. So the answers turned out to be incorrect, although the ideas were certainly there. Okay, so I'm going to discuss this point. I'm going to discuss what's going on there. That's going to probably take up most of the rest of the talk. I will see how things go. So let me give you a mini tutorial on absorbing state transition. So the standard example, and you'll hear directed percolation. That's the canonical example that is used in the statistical physics world, and people refer to this as the directed percolation problem, and the universality class is the directed percolation. I don't find that so useful to explain it to people who don't already know it. I find a much more natural example to use flu epidemics, because they are spatial temporal process, as this is a spatial temporal process, and the connection is much, much better in my opinion. So what I want you to do is I want you to think about turbulence as a disease, and so here's this turbulent patch, a puff, and I want you to think of it as an infection. And see there, that's me, so I am infected, so I have the disease, okay? So that's why I want you to think about it. All right, so what we know, what I've already showed you, is that if you wait a while, even though you're infected, I stay in bed, I drink soup, and then I get better and I go to the office, and I'm working again. And these equations, well, they would appear later, but I'm not going to get to that part. But anyway, that's what I'm working on, trying to solve this turbulence problem, okay? All right, now the thing is, so this is a space-time diagram of what I just showed you in this movie. It's not exactly the same state, but morally it is. So this is space-time. So that puff, that turbulent patch exists, robust. Again, it's fluctuating, but its intensity is more or less constant. Its speed isn't changing much. And then abruptly it decays, reverts to laminar flow. Okay, it recovered. And the thing is, it's statistical. If you run a bunch of different realizations, you'll find that when this occurs, it occurs at different times. All right, and I'm going to show you this because I think there's nothing like seeing it. So this is, I'm going to show you a simulation here. I'll just show you, and then I'll explain. So this is running, and this is pipe flow. Just take it to be pipe flow. And this top curve here, which you can see, that's red. That is the turbulence intensity, and it's 0 right now because I'm in laminar flow, okay? But if I have to, unless I kick it, nothing will happen. But I gave it a little kick there, and I generated one of these turbulent puffs. It's periodic, so it goes out that end and comes back in this end. But it goes for a while. The bottom curve, by the way, is let's just talk about it. So you see it went for a while, and then it reverted back to laminar flow. I'm back to laminar flow now, right? Okay. And I kick it again, and it goes to run. And you can time this with a stopwatch. Sometimes they last a long time, sometimes not so long. Well, while that's doing that, oh, it looked about the same here. Sometimes they're fast, sometimes they're short. Anyway, this other curve, by the way, is the mean shear, and that's going to come up again later. You see it decay. Anyway, so if you do a bunch of these, let me just pause it so I'm not using up all my CPU time while I'm coming back over here. again, you'll collect statistics, and you can get a survival probability as a function of time. So this is the survival function. How long, what's the probability that it survives up to a given time, 2,000 time units? And if you plot that from either experiments or numerical simulations, you find that's a logarithmic scale. You find they're exponential. Okay, so that they occur just randomly, but along this exponential. So what you can measure from this is a mean lifetime, and that is the sensible thing to measure. The life of this particular realization really doesn't mean anything. It's indicative of something, but it is not the thing to measure. The thing to measure is a bunch of them, get the distribution, and find the half-life, basically, the mean lifetime. Okay, how long on average do they last before they decay? All right. So that is the meaningful quantity, and that's one of the first things that it took a while to understand, is that you need to look at multiple realizations to get something meaningful. Oh, and let me just say something about that little simulation I was showing. That simulation I was showing was completely deterministic. It's exactly reproducible. Okay, I was changing the initial condition in the 6th digit and running different cases. Okay, that's otherwise they were exactly the same. And just if this means something to you, I didn't point to this before, but just in case it means something to you, if you have a billiard bouncing around in a chaotic stadium, and then you just put a little hole here and look at the escape rate from this, this will also be a memoryless Poisson process. And anyway, if that means something to you, that's the way to think about it. So it's deterministic, but it acts statistically. All right. Yeah.
I was just going to ask whether at Reynolds number of only 1900, a bit is critical.
Well, this is 1900 here. It's going to be actually below the critical value.
Yeah, but the probability that it will not be turbulent is going to zero.
Wait, you have to wait. Okay, I don't need this for the minute, but I'm going to need it later. This is the time to tell you that, as you would have guessed, the mean lifetimes depend on Reynolds number, and they grow with Reynolds number. As the Reynolds number increases, they're less and less likely to decay. They'll live longer. They still live exactly as these puffs, but they live longer at higher Reynolds number. Just put that aside, and I'll come back to it. Now, we're talking about disease, remember? Now, so this is, again, infection. But the disease can spread. So here I am. You think this is me as the disease. Right? I mean, as you know, there's a disease. This is me. I'm sick. I'm in bed. Right? But what can happen is that these puffs can often split off a daughter puff. Okay? It's known as puff splitting. Okay? So a daughter puff has come off. And so what you should think about that is, this is my daughter, and now she's sick too. Okay? So and we're all familiar with this idea, right? That's how diseases work. I'm not going to do this for you. It would take too much time, and it's kind of too obvious at this point, but you can measure, it's also statistical. You can measure lifetimes. You get distributions that are exponential. It's a memoryless process. Now, as you increase Reynolds number, they become, the time scales become shorter. They're more likely to split at higher Reynolds number. I'll show you this again later just to tell you we can measure those things. Okay, so here's the message. So, we have turbulence, and with some degree of randomness, it can either revert to laminar. That's just meant to represent a bit of turbulence. With some degree of randomness, it can go to turbulent flow, to laminar flow, or it can re-excite some bit of a laminar flow to multiply and now have two pieces of turbulence. Okay. And then laminar flow, on the other hand, is linearly stable. In the absence of noise and everything, it cannot spontaneously become turbulent. If you're laminar, unless you kick it, you're never going to become turbulent at these Reynolds numbers. I mean, eventually, practically any noise will drive you, but this flow is cannot spontaneously become turbulent. And this generically is referred to as the absorbing state, because if you get in that state, if the entire system is in this state, you will never leave it. It's absorbing. If once you're in it, you never leave. And this turbulence is generically referred to as the excited state. Okay? And these are exactly the conditions that Janssen and Grassberger were discussing when they discussed things like forest fires and epidemics and so forth. It also applies to turbulence, as I've just shown you. So again, let me just show you some generic behavior. It'll be immediately clear what it is because we know about epidemics. So the generic terms are the excited state, the active state or the excited state, and the absorbing state, which is turbulence or infection, laminar or healthy. I think that those ideas are clear, right? And the control parameter, I'm going to show you some little trivial model simulations in a model I'm not really going to explain, but just to communicate the ideas. The relevant control parameter is the rate of spreading divided by the rate of decay. Okay, so if R is big, it means you're spreading faster than you're decaying. If R is small, the other way around. Okay, so here are some simulations, and just so you know, it's a coupled map lattice. That's what the on-site dynamics is. It's a tent map with a laminar state. Anyway, it has all these correct properties, and I don't want to discuss it further. So I'm just going to show you two simulations, both starting with initial seed. So white here, so this is space. Time is going to always be going up here. Black is the active or turbulent state. White is the laminar or absorbing state. So this is an infection. So you infect some individuals here. I infected a few, and they spread. They infect their neighbors, and they recover, and they infect their neighbors. But if the spreading rate is small relative to the recovery rate, then eventually the epidemic dies out, and then everybody's healthy. And once everybody's healthy, that disease is never coming back. It's like smallpox, right? No more smallpox. And then here we have the infection has become endemic to the population. It just persists indefinitely in all time. Now notice it's not that one part of it's not that one individual stays infected. It's not that the population is I'm infected, you're infected, you're infected, and that's the way it goes for all time. No, it's spreading around in this complex spatial temporal way, and that's how it persists. Okay, so we're familiar with this idea, and I'm going to just show you that. And it doesn't matter about the initial conditions. It doesn't matter that there was a point you can do you can infect everybody and then just see what happens. Okay. And so let me just show you here, you can vary R a little bit more. Finally, anyway, what you'll learn from this is that there's a well-defined critical point above which you have, in the thermodynamic limit of an infinitely large system, infinite time, you will have the disease, the infection persisting to infinite time. Below that, with probability 1, the disease will not go to infinite time. Okay, and there's a well-defined point that separates these two. Here, the disease will necessarily die out before infinite time, and here, some will persist for infinite time. Okay, all right. Yes, if there's a question back there. Or? No. All right, and so do shear flows actually behave this way? Well, I'm going to just give you some hints about this. So we did this. This is the data that I showed you already about the decay and the split. I told you we could measure those time scales. So this is the mean lifetime as a function of Reynolds number. And this is the decay events. And these are the splitting events. And these are the time scales. And you'll see that they cross here at this point. And that point is 2040 plus or minus 10. And so the way you should think about that is at this time, so if you're to the left of here, the decay time scale is shorter than the splitting time scale. So if you start off with turbulence, you're decaying more. Your decay to laminar flow is more likely than your spreading, which means asymptotically you expect the flow to be just laminar. Above this point, this time scale is shorter than the decay time scale, so you're spreading more rapidly than you're decaying. So asymptotically, you expect the turbulence to persist here. Okay. Let me just tell for the experts, what I'm obviously not taking into account in this picture is that there's correlations that are going to begin to happen, which is going to change things a little bit. And let me just continue with that thought, again, for the experts. But these curves are super exponential, and the rate at which these things pass each other is so fast that within this plus or minus 10, the difference of the decay and splitting time is enormous. That's just these little details, but just those who worry about it. Anyway, so if you look a little bit above that critical point, you see exactly in these space-time diagrams the kind of thing I was showing you with the disease. So you have the patch, it's splitting, and there's some decay events, and again, the correlations begin to matter here, but the turbulence persists, and as far as we know, it persists indefinitely through this combination of process. And this is a way in which we can get at this critical phenomena by these measurements. And let me just say that we know that the 2040 plus or minus 10 is correct because that's what it says everywhere in Wikipedia now. Okay, so it must be correct. All right, okay. So let me just say a little bit more. So we can do more. I'm just going to flash this. I'll talk a little bit about this tomorrow, so I don't want to really do it now. But there's a lot more associated with this. Is just the basic idea. It was the first direct measurement of a critical point that really meant we correctly understood things we were working in a hugely long systems over very, very long times, things that people want to ask me about later I can talk about. But the thing is, there's other critical phenomena associated with these, and let me just give you a quick sense of that. So I already showed you this picture. So this is, the control parameter. This is a little toy model. This is not actual turbulence. And what you can see from this picture is that after I cross this critical Reynolds number in which the turbulence persists, or the epidemic persists, you can see that if you take an average, a mean, up here at some large time, and again, you have to be careful about make sure you're in a statistical equilibrium, et cetera, et cetera. But you could do that. You can see the turbulence fraction is increasing. You can just see it with your eyes, and it's intuitively obvious. And so the turbulence fraction is the right order parameter for this system. It is the right order parameter for this system. And what you expect, and what this little model will certainly show you, is that it grows, and it grows continuously, and it grows continuously with a very well-defined exponent beta. Okay? I'll come back to the universality in a minute. There are two other exponents. If you look now going to, decreasing R, what you can see again with your eye is this pattern is becoming sparser. Okay, it's becoming, and because space and time are not equivalent, they're kind of two characteristic scales. One is associated with the time intervals, and the other is associated with the space intervals. Okay, and those scale differently, but you can see that they diverge as you come closer to this critical point. So you can define, and I'm not going to worry about it here, you can define characteristic scales. We have a way to measure them. And you'll find that they diverge, hence the negative exponents, and there are a pair of those, one for the space and one for the time. All right, so there are three exponents, one scaling for the order parameter, and two associated with the characteristic space and time scales. And so these are the three scalings you have, and then you have many, many other scalings which are all derivable from these by manipulations. But these I'll take to be the three fundamental ones. And the thing is, and this really is a conjecture at this point, is that what Janssen and Grassberger said is that these ought to be universal, and they don't depend in any way on the details of the system other than its spatial dimension. Is it one-dimensional, two-dimensional, three-dimensional? But otherwise, it doesn't care about the details, as with many critical phenomena. Okay, and this has been observed over and over and over again in models. Yes, there are questions. Yes.
So when you increase
Yeah.
the Reynolds number and when you decrease it from some point, so there is some hysteresis in the turbulent fraction.
No, I'm sorry, I probably gave a misleading impression. All I'm saying is that I like to think of it, one is going up and one is going down, but no, all of these things you should think of as equilibrium. That is to say, I'm going to take a parameter value, I'm going to run until I get statistical equilibrium, make my measurements, and then I don't care, that will now be, it doesn't care whether I increase Reynolds number, decrease Reynolds number, et cetera. All it cares about is that I started with some black. That's the only requirement. I'll come back to the thing. I had to put some black in here. If I started with all white, there wouldn't be anything to measure. But once I put black in there, wait long enough and get equilibrium, there's no hysteresis, there's no history in this whatsoever. I mean, that's a...
Excuse me.
Yeah.
I have a difficulty understanding the space in your pipe. What is it? It's a center line space, or it's an area average? What is it? This is space. This plot, time versus space plot.
Yes.
So what is the space in the pipe? Like, how have you defined this space in pipe?
Okay, let me, can I look at this? Is this good? So this is a real simulation of pipe flow. So maybe I don't understand the question. So what you're seeing here is, I believe, streamwise vorticity. That would be the normal thing to plot in the pipe. Okay, so now maybe I can try to address your, so what you're seeing is black on the other things. This thing corresponded to one black dot in those little model pictures I was showing you.
So the space is the area average of the entire pipe length?
Yeah, okay, yeah, right. You're asking very good questions, and I should have addressed this. The scales that we're interested in here are very long on the scale of this phenomena, okay? So this, by the way, this is blown up by a factor of 2, but let's not worry about that. So this is roughly, the turbulence that you see in a pipe is roughly of the scale of 10 pipe diameters. So if you have a diameter of a pipe, the turbulence inside, its streamwise length is about 10 pipe diameters, okay? Now what I want to imagine doing is taking my pipe, and what you have to imagine is that what the pipe really looks like is more like this. It's probably thinner than that piece of chalk. It's 4,000, I'm not sure if I'm answering your question. It's 4,000 times the diameter is the length of the pipe. So one of these little patches of thing here, and this scale, looks like a little dot there, and that's where it's turbulent. So I've kind of collapsed mentally all of this to kind of just one discrete state. Either it's a turbulent puff or it's not. But I still don't think I've answered your question because of the way you're. But
No, what I try to understand, when you say that it's dying out at some time, some number, what I understand it, the Reynolds number is below critical.
yeah,
Turbulent is not surviving.
yes,
When you're saying it's not dying out, means it's above critical, it's surviving. When you're saying it's intermittent, it means that the distribution in the space is kind of somewhere spotty distribution.
that's right. That's exactly what. Yeah, you've got it. I,
That space thing was bothering me, like how you're defining this space by.
okay, yeah. So space here. This is the axis of the pipe. It's along the axis of the pipe. Sorry, that's good you asked this. But and I should have made that clear. But the pipes are going to be very, very, very long, and so I kind of I'm not worrying about the what I see through the cross section. I'm just collapsing all that to a single. Okay, I think I'll better go on. But also, all right. So, and I showed these
Some flows,
yeah.
some flows, especially flat plates, for example, the geos are all close surfaces.
Yeah.
Where those grow and how
Yeah. Right.
the mechanism is similar. We studied it at length. I don't know whether it has any relation to kind of.
Okay, so those in this community have spent, I'm not talking about the flat plate boundary layer. We would love to understand the flat plate boundary layer and understand how much it has to do with this and how much it doesn't have to do with this. It's a hard problem it's a developing flow, it's a hard problem, and it's still under work. Yeah. I'm only talking about the successes, not the failures. Okay, so I'm just gonna flash this. So, because it's not our work. So this is work that came out of Bjorn Hoff's lab. Really a tremendous set of experiments going on there. The first author is Grégoire Lemoule. And what they built, you can't really see this, is a Taylor-Couette device, but the fluid is essentially, it has a very long circumference relative to either the height, oh here, there's a little plot in here. The height is 8 times the gap is the gap, and the fluid is basically 3,000 times that. So it's very, again, as I was trying to communicate here with the pipe, the idea is, and I didn't really say this, we're treating this as one-dimensional. Obviously, it's a 3-dimensional flow. There's turbulence in here, but it's got one really long direction in which the fluid can explore this intermittency. Okay, and that's what this is. This is essentially a one-dimensional fluid. It's really turbulent in there. It's really, but it can only explore this one large dimension. Okay, and if this won't convince you, this is real experimental data. I mean, this is what the turbulence does. You have these patches of turbulence within the flow, and they're going along in this way. They're just like these little toy models that I was showing you. So it kind of percolates through the system. So this is, again, the disease. So the disease almost died out. If it had died out, it wouldn't, would have been over with, but it continued on. This is very, very near critical. And I'm not going to flash a bunch of log-log plots. You do a bunch of log-log plots, you do a lot of hard work. It's really a lot of hard work. And they find the critical exponents, and they find that they agree extremely well with the known theoretical values. Okay? And just to say, and I don't want to spend too much time on this, this is the first direct confirmation that this subcritical route to turbulence really is continuous via this very specific phase transition. And the way we know that, in particular, is that there are these universal exponents which that flow exhibits. Okay, there really is this way in which you understand it as being a continuous transition. And let me just say, if you don't do it that way, and maybe I can come back to this later, you're just going to be in trouble. This is what caused all this trouble at the beginning. I said about trying to define the critical Reynolds number. If you try and give some other definition, it just seems to be the wrong thing to do. And I'm going to say some more things about that when I conclude. Okay.
Just a little clarity. So when you showed the movie, right,
Yeah.
Previous slide, so each of those dots or each of those puffs is always moving in one direction, right, along the mean flow? Or do you have
Yeah, that's good. Yes, that's right. It is. It is.
Or do you see puffs with local phase speed in the negative direction? In these experiments, I'm just curious.
Okay. So, we have a long discussion about that. Puffs actually are moving upstream. But there's a mean flow, they're moving downstream. On average, they're moving about the speed of the mean flow. They're not moving at exactly the speed of the mean flow. That's kind of important that they're not moving exactly. But
slower or is it?
it's definitely slower.
And in the other direction.
And in the other direction. I would be interested in why you're asking that. That's a very insightful question. Okay, so yeah. You're taking this off my time, right? Okay, go ahead, sorry.
So when you said there matches the theory as in simulations of fluid flow DNS or a generic one-dimensional?
I'm talking about one-dimensional DP models, what we know from one-dimensional DP. We cannot.
Or simulation of the DP model, the calculation.
I'm kind of unclear on that because I think they're only known numerically. I don't think anyway. I mean, they're irrational. Those exponents are irrationals, and I think they're only known to finite precision from. That's my understanding. You can read that in Wikipedia. All right, so I'll talk about this tomorrow. I'm not going to say it now, but with Matt Chantry, and he really did it all. We needed, so that was a very nice work on a one-dimensional problem, but I told you it depends on the number of space dimensions. And so we wanted to look at a planar shear flow, which I'll consider a two-dimensional problem. Let me just show you. These are this kind of intermittency in one of these planar flows. Again, you're looking at it on, there's a wall normal direction, which you don't see here. This was the largest numerical experiment that had been done to date. And this is the largest physical experiment that had been done to date. And those are perfectly fine for understanding what you see in this figure. But the thing is, Matt had to work out a way to go to much larger domains, and even this is kind of marginal. So that's fine for this here. But the thing is, this turbulence becomes very, very sparse as you go close to criticality, and you have to be able to resolve things like this. And I'll tell you more about that tomorrow. Okay. Okay. So let me. So I have still a good 10 minutes, right? Is that right? Oh, okay, okay. All right, so yeah, all right, I'm trying to think of how I want to do this. This was a blank slide in there to make me think. All right, so I don't always explain things the same way. So let me say this. What I've been describing is, how you think about going from laminar flow to turbulence, well, again, let me just summarize a few ideas that we've had. One is that for a long time, it was thought that these things were just noise-driven, imperfection in experiment. We know that that's not true, that they are very, very much, they act statistically, but they are definitely deterministic phenomena. And again, think of a billiard bouncing around. This is a completely deterministic phenomena, but it acts like a memoryless process. So that's the way these things are. And this really provided a lot of clarity in trying to understand things like what is a critical Reynolds number and so forth. It really, until this occurred, there was huge fights about this. And now all that has gone away. We at least understand the context in which we should be asking the questions. Okay. But from a fluid mechanics point of view, that's not the important question. I mean, that solved, that stopped a lot of fighting. But it doesn't really explain why there's intermittency in the first place, which is really the more important question, because I told you that these phenomena were universal. They happen in flow through porous media, they happen in disease epidemics, they happen in forest fires. Well, if they happen in all those systems, well, how could it not happen in this one? I mean, there's pressure, there's a global problem, I mean, there's reasons not. But the thing is, why did it become intermittent in the first place? Because once it's intermittent, then probably it had to obey the universality. So the question is, why is it intermittent in the first place? I believe that that's the more fundamental question, and if you understand that, then everything else will follow. Now, yeah.
Does it also follow why there isn't intermittency here?
Why there isn't? That's a good question. Maybe. Yeah, you guys ask a lot of good questions. Yeah. All right, yeah, put that aside. All right. Here, let me go back to this. Let's play with this a little bit. So this is my simulation. And again, so let me just remind you what I was doing. If I give it a little kick there, I can generate one of these puffs.
This is, what do you simulate?
I'm going to show you. So so this is a simulation of one of these puffs, and then as I showed you, if you I didn't actually run this in the model, but let me just show you this. This will split. See, oh there, see it puff splitting? I told you, I've increased the Reynolds number. Now it went from 1 to 2. Does everybody get that? And now it is at 3, right? So this is this splitting phenomenon. So I'm in this intermittent regime. So this eventually will kind of fill up this geometry with these patches, and they'll kind of decay and spread and kind of keep in this intermittent thing. And you can compute the statistics of this, and you find that it obeys a percolation transition, a directed percolation transition with the critical exponents. Okay, so that's the thing. But let me just say that I wanted to show you with this. If I increase the Reynolds number further, and I hope I did it about the right amount, and I give it a perturbation, what happens is that perturbation just spreads, and it just takes over the flow. It just becomes turbulent everywhere, okay? And this is what most experimentalists in pipe flow do. I mean, they probably don't even bother with the perturbation, because if you work up at high enough Reynolds number, the perturbation that you need is practically the scale of your, the defects in your experiment, and you just simply jump up to the turbulent branch, okay? The thing is, then, if you bring down the Reynolds number, just say, you'll get back to this intermittent state, okay? And the question is, why did it do that? That's one way of looking at it. Forget that I came up from below. Why does it do this? Why did it become intermittent like this? And I'll give you a hint. So there's two things here. That's the turbulence, and here's the mean shear. So let's talk about that. Again, I'm going to pause it so I don't use up all my computer CPU time. So let's see if we can explain why there's intermittency. So for that, I need to show you two things. So this is what we've been discussing up to now. This is Reynolds number 2000. This is this intermittent state, just one patch of turbulence, a puff. And again, this is space and this is time in a co-moving frame. These things move downstream, but I'm looking at a co-moving frame. And just to answer your question, this speed, co-moving frame at Reynolds number 2000, this is in the frame of reference of the mean flow, and it hardly moves at all in that frame of reference. Okay, so asymptotically, I have one of these or multiple of these, and that's the intermittent state. If I go to high Reynolds number, the turbulence, what I just showed you, the turbulence will just spread and fill out. And again, this is all moving downstream, but we're co-moving with it, so we see it spreading both ways. And then you get to this, and this is what you just call turbulent pipe flow. That's just what, as in Steve Pope's book, okay? So I want to understand these two, but I really want to understand it in this spatial temporal way. I don't want to just say this and this. I really want to talk about this. Okay, that's why I'm showing you these. All right, so it's easy to understand. Oh, I didn't say the words. Let me say the words. This is called a slug. This is called a puff, as I've already said. This is called a slug. That's just the word that's used. I can't help myself. I will use that word. Okay, so we can understand a slug very easily. All right, so upstream, there's laminar flow that looks like this. Let's see what that's going to. And you should think of this. This has a high centerline velocity. There's a lot of kinetic energy in this laminar flow. Okay, there's a lot of kinetic energy in this laminar flow, and it's going to flow into. It's moving relative to this interface. You saw that before. That interface in the frame of reference of this mean flow. This interface is moving that way. This front is moving into it. So anyway, these two are moving together. And what happens is, right at the beginning, and you can see the intensity of the turbulent. What you're seeing here in colors is the turbulent kinetic energy. I should have said that. That's the turbulent kinetic. And you can see it's really intense there. Production exceeds dissipation there because you have all this, basically a source of fuel, which is this upstream laminar flow. There's a huge amount of kinetic energy in there. It comes in there, you extract kinetic energy from the mean flow and put it into the turbulence. Okay? And then what happens is that because you've extracted kinetic energy from the profile, you've blunted the profile to a typical turbulent profile. This is just a sketch. Okay? You blunt the profile, and then you reach this equilibrium downstream where the production is equal to the dissipation. Okay? And I really, really want you to understand that this is an equilibrium, and you can write down Reynolds average and average Stokes equations. Okay? You write down Reynolds average, I'm not going to do it. You'll find the production term is just this. It's a product between the mean shear and this component of the Reynolds stress. And this is the only term that enters into the production. And again, in case people aren't experts, the word is used as production, means you're producing turbulent kinetic energy, but really it is a transfer. What this is doing, it's taking energy out of the mean shear and putting it into the turbulence. So from the point of view of the mean shear, this is you're losing energy by this, but that's what this is. So it's an equilibrium set up between this shear profile and the turbulent fluctuations that just exist forever. And again, This is extremely well understood. It's been known for a long time. Just open up Steve Pope's book. You'll have a complete description of this problem. Okay? You can't analytically solve for these things, but numerically we know what they all are. Okay, so again, that's the equal. Now, what happens when we turn down the Reynolds number? When we turn down the Reynolds number, that means we increase the dissipation. The production doesn't care about Reynolds number, not directly. The dissipation does. There's a factor of viscosity in front of it. Well, what happens is this equilibrium is lost and it's gone. However, you can see that this, where production exceeded dissipation up here, that does not die at the same place that this does. So this equilibrium is lost, but you can still maintain this upstream intense front. Okay? And so that's what a puff is. It's just what remains of this turbulent slug after that downstream core is lost. And you can see it very clearly. There's lots and lots of ways you can see it. This upstream front is just what survives and becomes this. That's all it is. So you lose this downstream equilibrium.
Can that be predicted theoretically? Or is it like computational result?
It's a computational result. And that's a problem under consideration, is to do a much better job with that.
So can you go back to the slide that shows the different, okay, all right, so this is interesting. So why is in the slide, this is a computation, right? Okay, so why is that the burn front, right? Why is that not symmetric on both sides?
Okay.
Or the intensity of the burn?
Yeah. No, you're right. Okay, so what happened, there's a whole long story here too. This undergoes a couple transitions in the process. Asymptotically at large Reynolds number, these two burns do become the same. Because what happens here is you're overrunning downstream laminar flow, and exactly a symmetric thing happens to upstream. But in between, this front speed, the difference in the local advection speed changes that picture. The fact is that this is, well, my arrows are none here. The fact that there is a difference, I have flow coming in here like this, so they're not symmetric. So a transitional Reynolds number is right when this first forms, it is not symmetric front to back, but asymptotically in large Reynolds numbers it becomes.
So should I think of it as the relative velocities, whether it's moving upstream or downstream, is affecting the local shear somehow?
Say it again?
Should I think of it as the relative velocity, the change in relative velocity, whether it's moving upstream or downstream, is affecting the local shear? Because
that's probably a good way to say it. I'll certainly say whether it's, yes, that's right.
The slug itself would affect I mean, it's a two-way coupled problem, right? Yep. It's not that the slug is removed from the local mean.
That's right. Exactly. That's right. Yeah, you guys are right. Very good. Yeah. So here's the thing. So I think you got this. What a puff is. It's just the upstream front that remains after you lose the thing. But what is key, and what I told you essentially, was that the mean shear profile provides a negative feedback mechanism, providing the localization. It's the fact that here I have this. When this goes through, when kinetic energy is extracted, that blunts this profile, and it blunts it to the point that this turbulence can no longer extract enough kinetic energy out of this mean to sustain itself, so it decays. Then once the turbulence is decayed, then that laminar profile can recover. Okay? And I'm going to show you a movie, and I hope it's clear enough here. To me, this makes it just so clear, but it's whether you can see it or not. So this is, again, a movie by Bofang Song, who did much of this work. And that's a high Reynolds number turbulence state. You see it's not completely uniform. And then what he did is he dropped the Reynolds number, and let's just watch it, and then I'll point to some things. And you'll see that you could have imagined the whole thing just collapsed. You know, all the turbulence went away to zero. But in fact, it doesn't. It forms these localized patches. Now, they seem to have come out rather evenly spaced. That's not always the case. But let's just think about what's going on here. The thing is, at this Reynolds number, if you tried to put turbulence everywhere in this pipe, there would be too much dissipation. There would be too much dissipation relative to the pressure drop, and it could not sustain itself energetically. It would collapse. However, it can sustain itself in this state, and the reason it can is because here's turbulence, and look what happened. Here the flow, there's no turbulence here, so there's less dissipation. The flow can re-accelerate. You can re-energize the flow through that acceleration. You're extracting energy from the pressure gradient. You're not spending any energy, in dissipation into turbulence. So you can re-energize the flow here. That provides a nice source of energy, and then you can burn some more. Okay, so you can, that is how this works, and it's why it works. It's because there are these two variables, and that with a negative feedback. Okay. Now we'll see, let's take a look at this. Does this remind anybody of anything? Yell out if you don't. Does anybody here work with, say, the brain or the heart or anything? Does that remind you of anything? They're action potentials. These are action potentials.
So this particular plot and these videos, they are a model?
This is a model. I've been not so clear about that. I was going to make.
1D model?
It's a 1D model. Okay, so I find this remarkable that this has not been known for 100 years or 50 years, but it doesn't seem to be the case. That if you look, this is actual data from a pipe. This is not a model. This is a cartoon representation. But I have one of these puffs, and there's a sharp peak in the kinetic energy in the flow, and then the profile gets blunted, and you have this localized patch here. Again, the two variable thing. And what does a neuron do? Again, if you don't know about it, well, I think everybody knows the basic thing. They have action potentials. A signal, electrical signal propagates down the neuron. It's a depolarization between the inside and the outside of the axon. So you measure it as a voltage, and that's what it looks like. And it's local. All right, and so let me just go on. So look, we really have the situation. Many, not all nerve cells are like this, but that they will sit there in this unexcited state for as long as they're kept alive. They'll just sit there like this. Just like pipe flow, laminar pipe flow, say at a Reynolds number right about here. Turbulence is possible for it, but it will sit there, and if you start it in the laminar state and don't kick it in any way, it'll just stay like this. Right? But if you do kick it, either one of them, if you kick the cell by having a signal come in from a neighboring cell, you'll excite this action potential, and in this case, in the case of pipe flow, likewise, if you kick it, you'll excite one of these. And there are really strong analogies between these two, and in these kind of problems, and I'll point you to an abstract that was just a talk that was held yesterday over there. There was work on this in excitable media. Again, if you're not familiar with this, just try and take it in a little bit. We know that either you can go to the full physiological models. This is for cardiac, your heart's also an excitable medium. I'll get to that in a minute. There are waves propagating through it. That once per second wave that goes through your heart is basically like a puff. All right. Anyway, so there's the detailed physiological models, which you should think of as kind of like the Navier-Stokes, but you can capture the essence of these things with simple two-variable models. There are two scalar variables here depending on space. One is the voltage, and the second is a gate variable. And what I want you to think about that is we can do the same thing for this pipe model where we have one variable is the turbulence, and the other is the mean shear. Now, I know mean shear, you have to say what you mean by that as a scalar representation, but that's the idea, that we're just going to map all this down. And I'm not going to say anything more about it. I've written a lot of papers about it, so if you're interested, you can read those. But this model, which is essentially just an excitability model, is what I've been simulating up till now. And here's, again, the basic idea. And I'm not going to explain in full detail because I don't want to, but and bore people or whatever. If just try and take it in if you're not yet familiar with these ideas. So this is my slug, all right? And this is a model, and this is the mean shear, or and I have just a scalar representation of that. And I'm not going to worry too much. And this is the turbulence, and this state here is a fixed point corresponding to laminar flow. The turbulence is 0, and the shear profile is fully recovered. Just think of it that way. And that corresponds to being up here in physical space, that dot there. Then as I come through this, this slug, what happens? What happens is the turbulence increases like this. The turbulent intensity increases. As a result of that, the shear profile blunts, and I end up there. So the turbulence increases, the shear profile blunts, and then I reach this nice equilibrium downstream. And that is that process. And I reach this nice, stable equilibrium there. In the case of a puff, what happens is, starts off the same. I have this laminar fixed point, and then I hit the turbulence. The turbulent intensity goes up. The shear profile blunts. But I no longer have an equilibrium accessible to my system. So what happens is, the turbulence drops back down, and then eventually the mean shear recovers. And that, by the way, is the way an action potential works. Okay? And so, oh, there's my arrows. So I have this excitable case, which is the localized state, the puff, and I have the bistable case, which is the slug, the thing that fills the pipe. And yeah.
Can you please explain again the possibility of multiple slugs? Where is it getting the energy to generate
Yeah, okay, so let's see if I can do it with just this picture. Yeah, you can see it here. So there is, see when this shear you see that? This one has, and you can work it out, but now I've forgotten. So let me not give you a number, because I don't want to tell you the wrong number. But this has quite a bit more kinetic energy than this. You have to realize kinetic energy is the square of the velocity. And of course, I know that this is radial, and so you have to take into account the relative volumes, and so that's why you have to be careful with the answer. But this actually has quite a bit more. I believe it's about a factor of 2 more kinetic energy in it than this. It's just simple acceleration of laminar flow down a pressure gradient. Oh, you're talking about in this or in real pipe flow? In real pipe flow, there's a pressure gradient here. And the pressure gradient is accelerating the flow. The whole thing is driven by a pressure gradient. What is going on in a pipe is I have a pressure drop here. From here to there, I have a pressure drop. Okay, everything that's going through that takes place in between is getting energy out of that pressure drop, and it's either coming out the end with kinetic energy or it's dissipating it inside. But one of those two things has happened to the kinetic energy. You put in potential energy, there's a certain flow rate, so there's a certain power going into it, and that power goes someplace. Either it comes out the other end or it's lost to heat.
How is the daughter splitting?
Because what I'm saying is the transition is captured by excitable to bistable together with fluctuations that you have to put in fluctuations on the upper branch. And then this is a whole another talk about how do you put in the fact that this is not fluctuating, but this is, and you can either do it with multiplicative noise, which is kind of formally the easiest thing to do, or you can do it deterministically, which has a lot of advantages, but you've got to put in the fluctuations. But you have a nice thing, you can look at it with or without fluctuations. And I want to end because I don't want to keep people here too. But the thing is, with these ideas, you can reproduce essentially every known phenomena in the pipe flow transition problem. This is reality, meaning either experiments or direct numerical simulations of the Navier-Stokes. This is this simple model. This again is reality, the crossing point, things I did not talk about, and then this is the model. And I'll just tell you, it gets the speeds almost exactly correctly. There's a lot of details in those speeds that you were asking about. Okay, I'm just going to say just a word about this, because Nigel is a colleague of mine. We talk about this all the time. I'm not talking behind his back. I want to say this because I know he's going to come here sometime in the future. We disagree on this. I told you what I think. I think I have a tremendous amount of evidence on my side. Nigel is claiming these phenomena are due to zonal flows. I completely disagree, and I think there are many problems with the zonal flow point of view, and I'll be happy to discuss that privately. Again, I'm not talking behind Nigel's back. He knows I disagree with him, and I just don't think it's right. I think it's not right. So let me end on something lighter. So again, I want to show you something here. This is, so I told you, the heart is also a excitable medium. This is Grey's Anatomy's season 1, episode 1. Meredith Grey saves the patient. Boom, okay. So now I don't know, this is gonna be really hard for you to see. Can you see that or not see it? Can we turn off the lights? I don't know. Anyway, yeah, so I know this is a TV show. I know that. But nevertheless, it's pretty accurate. So that's, to save the patient, the heart went back. Those localized things that you see on the EKG, those are really these excitable, the fact that the waves going through your heart are localized is for exactly the same, I mean, not the same physics going on. One is electrophysiological, one is fluid dynamics, but the same negative feedback between an excitation variable and something that cuts off that excitation variable is really the same. And you could just, property after property, you can map one onto the other. You get the speeds. Everybody in neurophysiology knows exactly how speeds behave and what the dispersion restitution is, and these behaved, and puffs behave the same way. I just want to say that, and it's a little fun. Okay, I'm going to conclude now because I don't want to keep people here too long. So I've talked about this, and particularly about the idea that in these spatial temporal complex systems, we really do know how to now understand them through this critical phenomena. I also claim that we understand a lot of the physics which gives you this in the first place. And we understand that really it is a very good way to look at it as opposed to the way that those systems, I'm not trying to put one over the other. I'm just saying that this approach is really kind of necessary when you have these kind of phenomena. These strongly subcritical systems in which the turbulence behaves the way it does here. And I think it's useful to think about this. look, if you want to, everybody can understand this. If you want to understand forest fires, okay, you know, you're not likely to sit there and just watch. It's not a good way to understand forest fires. You know, you have to light some trees on fire if you want to understand the way forest fires work. You know, and if you have a strongly subcritical system like these, you know, you have to introduce perturbations and then see what happens. And this is what we learned, is that you inject, you wait, the thing is you have to wait a really long time in a really long pipe, and then till you reach a thermodynamic equilibrium, I mean a statistical equilibrium, and then you measure the statistical properties. That is the way in which you can understand these systems in a way that you don't cause all these arguments. Okay, and it's really brought tremendous clarity to our understanding of these problems. And the other thing is, again, there's a whole class, you know, the people over here, I mean, maybe some of you are those people too. I mean, the statistical physicists have known this for a long time. There are many, many, many examples of this. So why wouldn't you just put it in that natural class with all that understanding that already comes with it? And it's a beautiful confirmation of these scaling laws that were predicted long ago. And I'll just end with this very last thing, is that, you know, this must be the right way to look at this. And I'm going to give you a quote from Osborne Reynolds from 1883. And it's really remarkable that Osborne Reynolds said this. I'm going to read it word for word. I'm going to read it from here. His language is not the best, but so I'll have to translate a little bit, even though it's in English. Okay, it became clear to me that if in a tube of sufficient length, again, it had to be very long, much longer than he thought. If water were first emitted in a high state of disturbance, i.e. you're going to have to disturb the flow, that's the right way to do it. Then as the water proceeded along the tube, wait a long time, the disturbance would settle down into a steady condition, which would be either one of eddies, which we would now just refer to as turbulence, or one of steady motion, laminar flow, according to whether the velocity was above or below what might be called the real critical value. So that's exactly the description of directed percolation and everything I've told you, that you have to introduce the perturbation, you have to wait, go to some thermodynamic time, and then see whether you have turbulence or not, and measure those things. And when you do that, you get a real critical value. And with that, I'll thank you.
So I remember a few years back I come across some literature that talks about exact coherent solutions for the Navier-Stokes equations when you're not fully laminar, neither are you fully turbulent, right? So those states, the puffs and the slugs, is it the same thing?
Okay, so that is that's an important thing that I didn't discuss because there's so many things. Yeah, there's certainly a lot of overlap. So I would say that those ideas are trying to understand, if you just kind of pick a random figure in here. Let me pick this one. No, yeah, this. So in other words, this is quite a complex object, even though it's relatively simple compared to a lot of things. And you would like to understand why, why does the turbulence have certain, length scales and things like this. And one way you can understand it is by seeing that embedded in here are some simpler structures that we can get at exactly in these methods, or even in the interior of this pipe. And so they provided a lot of insight to this. They provided a lot of insight into the boundary between turbulent and laminar flow. They don't seem to, at this point, and they do begin to say something about the localization, although I would criticize, they reproduce the localization, let me say it that way. But what they, the question is that they don't see anything about if I have two puffs, or if I have one puff going to two puffs, or if I have one puff dying. They don't really address that problem, and that's really what you kind of have to. So there are certain things they do tell us things about, and other things they don't tell us about. And most of what I talked about today, they don't have much to say about, which is why they didn't come up in my talk. I think they're very valid, they're very interesting, but they just don't, I don't think, contribute much to our understanding of the percolation phenomena. I think we should, oh, yes. Okay.
So the mechanism you talked about, is it directly connected to the non-normality of the system?
Laurent, do you remember Fabien's answer to a non-normality? He says, yeah, it's
So the answer was, of course you have non-normality, and so what?
No, the point is, the thing is, a non-normality is throughout all of this because the operators are highly non-normal. It's not really, but hold on, yeah, okay, right. I would say the distinction is nonlinearity. I say it's the nonlinearity, it's by far the important thing. It's not, I would just say, in fact, I think you can probably find two systems whose operators have the same pseudospectrum, I mean, same degree of non-normality, and one behaves this one, that's a conjecture. I don't know that that's true, but it's not the non-normality. I mean, it's going to be non-normal, but that is not the key distinction.
Actually, that's question.
Yeah.
My question.
All right.
So, in terms of the mechanism that produces the puffs, do streamwise vortices, do they play a role?
Yeah, but this gets back to the thing. I mean, just to say that these exact coherent structures tells a lot about streamwise vorticity and how that plays a role. And I agree with all that, by the way. But the thing, this is okay. What I'm claiming is really crucial here is the spatial. When I shouldn't take it out of my box, I can show you plots of we have all the energy balances and everything going through these puffs and through these interfaces. And the thing is, what is going on here and a long ways here is very different from what is going on here. It's a spatially very inhomogeneous situation. And not only is it spatially inhomogeneous in the streamwise direction, the way that shear profile bends is going through there is really quite complex. So the thing is, I'm sure you could, I mean, it's a legitimate question, it's just not known. How do the streamwise vortices and how does that picture, what's that have to do with here? Because people talk about the shear layers, you could see these things are slightly distorted in the shear layers. So there's a lot of things there. I mean, if you look at one of these, just after that, you're going to see a lot of streamwise vorticity, and you're going to see a lot of these rolls in those structures. That will always exist in a wall-bounded shear flow, but I think it's so spatially inhomogeneous that there's a lot more going on. Yeah.
When we talk of intermittent turbulence,
Yeah.
now I come to I'm more interested in quake flow.
Yes.
Now, the quake flow is re-established fully after the intermittent the puff that you generate.
You're talking about plane quake flow.
Yeah, the quake flow.
Yeah. Well, okay. Yeah.
Because it fosters the development of certain bacteria from the microbiological point of view.
Yeah.
And agglomeration of particles.
Yeah. Okay.
Because I have conducted such experiments. So now, after the intermittent turbulence regime, is the quake flow truly fully established?
Yes, but from what I understand, I'm not an expert on this, but from what I understand from pictures, and Lorette may have something to say about this too, is that you can see, I believe, if you're talking about, say, circular Couette flow, I believe that it really quite high, and this goes back a long time, I believe even Andrek and Swinney noted this, is that you can see some kind of large-scale pattern, when this flow has become very, very highly turbulent, there's still some structure in that turbulence, it seems. I see you nodding your head. Yeah. So it certainly ceases to be intermittent, and it's fully turbulent, but I believe that I believe that there's still, one sees some structure in that turbulence that is not just, no, I don't, okay, let me say I don't know. It's easiest to say I don't know. But yes, I believe, you turn up the Reynolds number large enough, and yes, it becomes fully turbulent.
Do you think the vorticity dynamics point of view can like how they are dying and stretching some sort of when there is a favorable pressure gradient, some sort of intensity for a while and then point of view.
Okay, let me say this. I think that if I understand your question correctly, I showed you some model simulations based on some very simple ideas in fact, I'll just go to here. And I was asked about this. I showed you some very simple ideas with these pictures. And then what I said, because I did, is that you need to add some sort of fluctuation. I believe that you need those fluctuations in order to have the decay events, the spreading events, all those things. Those fluctuations have to be there. And to this point, the way we have added those fluctuations is either with multiplicative noise or with a certain kind of map models that are reminiscent of that. And I think there's a lot of fluid mechanics that I'm ignoring that almost surely has to do with vorticity and other things that would explain what the nature of those fluctuations is. I've just treated it as kind of like a noise problem, but it's not. Maybe people want to go, though. Maybe we should end.
I just don't know all that. Some questions. So let's just thank the speaker.
Okay. Thank you.